I expect you already knew this. Special Quiz 3, at long last, was completed yesterday afternoon and posted. So please get at such. As I said before, the indicated due date on the quiz is next week Wednesday at the start of our last official discussion class. But if you feel the need for some extra time, I can extend that to a week from today. Given that, I will, as per usual, offer a review for the final exam. The review will span 2 periods. I will obtain a room and announce such to you. And for the review, it will be your responsibility to stimulate review by simply asking questions. Questions which follow from any past quizzes or exams, from the notes, anything we've considered this term, all of which will be fair game. After you ask the question, I'll take over. I will also, to try to make things as convenient as possible for review, bring with me exams 1, 2, 3 from this term and finals from the last couple of terms. Because more often than not, the questions which are asked during these review sessions come from those exam activities. But any question you want to ask about chemistry regarding this activity is fine. If you go back a few years on an exam or quiz, that's fine. If you simply read the question loud enough and clear enough, I'll know what's going on. After all, students often come to me in my office to ask questions about such things, and they say, "What do they want?" They. I wrote all these questions and problems, every one of them. As I said, I make a point of designing each quiz and each exam that I give as a brand new activity. Under no circumstances, as I have taught this course, going back to the early 80s, I've never yet given the same quiz or the same exam, and I have no intention of ever doing such. Why should I get stale? That's no good. And beside that, every time I go through this course, the material continues to evolve. I get at it in greater detail, recognize considerations which in the past have not yet been recognized, and it's my intention to share all such with you. So if I were to put to use past exams and quizzes, those exams wouldn't contain questions and problems on this new stuff. And I'm not going to waste the time to go to a past exam or quiz or say, "Oh, well, there's a good question, I could use that." Hell with that. Okay, our bag of tricks, the factors which we must consider to be able to assess the strengths of Bronsted-Lowry acids, which we do in terms of assessment of effective negative charge density of the conjugate base of the acids. Because by conjugate theory, as we well know, when we know the relative strengths of a series of Bronsted bases, then immediately we know the corresponding relative strength, which is the opposite strength order for the bases. We immediately know the strengths of the corresponding conjugate acids. Last time, we finished with some considerations in regard to induction, which we found depends on length of covalent bond skeleton. Inductive effects or inductive stabilization of negative charge is inversely proportional to the length. Length? The hell is that? of covalent bond skeleton. The longer the skeleton, the less effective is inductive stabilization of negative charge by atoms of high electronegativity, which because of the length of the bond skeleton are separated from the site of negative charge development by H plus loss. Then orbital electronegativity, which you've already considered. As another consideration, hydrocarbons. Hydrocarbons are notoriously weak acids, but still their strengths have been investigated by organic chemists because it's often necessary, well, I shouldn't say often, but on occasion it's necessary to get a hydrocarbon to react with a really powerful base to provoke the hydrocarbon to convert to an anion, the conjugate base of the original hydrocarbon, which is achieved by getting the original hydrocarbon to lose H plus to this really powerful base with which the hydrocarbon has been reacted. You'll do stuff like this in organic class. If this loses H plus, you get this. If this loses H plus, you get this. If this loses H plus, you get this. Now, as I usually don't do, I've sketched the electron pair, which previously was connected to H as H plus, as a non-bonding pair with dots. I usually use a stick, but just to be sure we recognize the presence of this developed non-bonding pair on carbon, I use the dots this time. As bases, how do the strengths of these bases compare? Well, it can't be an issue of straight electronegativity, because in each case the negative charge is on a carbon atom. It can't be an issue of induction, because hydrogen atoms don't stabilize negative charge at all by induction. After all, hydrogen atoms have a lower electronegativity than carbon. So if there's a difference in base strengths between these three anion species, then we got to go deeper. We got to look someplace else to get an explanation. The explanation used is that of orbital electronegativity, which you talked about, as I said already. Now then, we can talk about atomic orbital electronegativity, SPDF, if they're all in the same energy level. Which of these orbitals has the highest orbital electronegativity? S. That's where the electrons would go if they had the opportunity to go someplace. Because on a time average basis, because of penetration, the s orbital is not only further from the nucleus, it's also closer to the nucleus. Which means even though electron density in the s orbital, the highest n value s orbital, defines the size of the atom in question, S electrons are most difficult to remove when you go about the business of ionizing the atom in question, because again of this penetration effect, which we talked about last time. Now when we get to hybrid orbitals, if you go about the business of hybridizing the orbitals of period 2, the game is easy. Because in period 2, you only have two types of orbitals, S and P. If you go to period 3, it gets more complicated. Because in period 3, we also have valence d orbitals. Now, when we get to period 4, we have valence d orbitals as well as valence d electrons. So if d orbitals are part of the valence state, how many hybrids can we create for the various valence states shown by an atom which has valence sp and d orbitals? sp, sp2, sp3, and that's all we can do with the s and p blends. Because when we get to sp3, we've used all the p orbitals for that are in the p orbital of the sublevel in that energy level. And now we start mixing up with d's. sp3d, sp3d2, sp3d3, sp3d4, and sp3d5. How many hybrids has that given us? 9 of them. Which of these hybrid types, for orbitals taken from the same energy level, which of these hybrid types has the greatest orbital electronegativity? Which one? Which one is it? SP. Why? It has the highest percent S character. No more, no less. And which of these hybrid types has the lowest orbital electronegativity? sp3d5. Just a simple arithmetic game. Pay attention to the percent S character of the hybrid orbital. The higher the S character, the greater the orbital electronegativity. So let's apply that to this. Hybridization-wise, what's this carbon? What is it? I'm hearing some faint responses. At this stage of the game, you should be able to look at these Lewis structures and immediately know how the atom in question is hybridized. How do you determine hybridization? You count the number of sigma electron pairs in the valence environment of the atom in question for the Lewis picture. That's all you have to do. With one exception. We're going to talk to you about the exception in a moment. Just so you, at this stage of the game, will now get at this exception. Okay? And non-bonding pairs are always part of the sigma framework. And at a covalent bond site, like this covalent bond site where we see a so-called triple bond. How many of these bonds are sigma? One. All right. So, a sigma pair and another sigma pair. How many orbitals do you need to provide parking place for an electron pair in a nuclear force field? Pardon me, to provide parking space or parking places for 2 valence sigma electron pairs? 2. So how many orbitals we got to blend? 2. sp. 1, 2, 3. sp2. And 1, 2, 3, 4. sp3 done. Which of these is the most stable base? Let's call it A, B, C. Which is the most stable base? A. So which is the weakest acid? This? No, that's the strongest acid, isn't it? Because its conjugate base is the weakest of these 3 bases, because this conjugate base is the most stable of these 3 bases, because the non-bonding pair is stabilized more effectively by an sp hybrid carbon than by an sp2 hybrid carbon, but which stabilizes electron density more effectively than sp3 hybrid carbon. Because this is only 25% S character, this is 33 1/3%, and this is 50%. That's it. All right? Resonance. Well, we're going to show you this so-called exception in just a minute. Don't worry about it. Resonance. Acetic acid molecule. The acetate ion. A species formed when acetic acid molecule does its acid thing, given that behaving as a Bronsted acid, the acetic acid molecule never loses any of these H's as H+, which we've already discussed. Remember that? Hey. This thing, putting a negative charge on carbon, creates a very, very reactive, a very unstable anion species. Which keeps with what we said about these. These are very lousy acids at best. These are very potent bases. This too would be a very potent base. So when you get the acetic acid molecule to lose H+, it only loses this H as H+, which deposits a minus charge or creates a minus charge on oxygen, and oxygen, being an atom of considerable electronegativity, stabilizes that minus charge effectively. But what's really interesting about the behavior of the acetic acid molecule, I think more so than stabilizing the minus charge by the highly electronegative oxygen atom after the minus charge has been created by proton loss by the parent acid, is if you could see the acetic acid molecule, which you can see with spectroscopic observation devices. This. How does the length of this CO bond compare to this CO bond? For the acetic acid molecule. How do these bond lengths compare? Is one of these bond lengths shorter and stronger?
Yes.
You're damn right. This one. This is a carbon-oxygen double bond. This is a carbon-oxygen single bond. But when this thing loses H+, what happens to the difference between these bond lengths and strengths? They equilibrate. They become identical in bond length and strength. They now have a bond order of 1.5 from an arithmetic standpoint. But what's interesting about resonance is not only that it creates this identical covalent bond nature, is a resonance stabilized covalent bond is somewhat more stable. Than a bond whose strength would be calculated by taking the bond strength, the bond energy for a carbon-oxygen double bond, adding it to the bond strength, the bond energy for a carbon-oxygen single bond, and dividing by 2. Because arithmetically, that would give you a covalent bond with a bond order of 1.5. But when you, by experimental methods, observe the carbon-oxygen bond strength for species like acetatide, you find that CO bond strength is somewhat stronger than what you get by doing what we just said. Taking CO bond strength for a CO double bond, CO bond strength for CO single bond, add them up and divide by 2. Okay. Now then, to an extent, you'll be asked to play games like that on SQ3. How many of you have looked at SQ3? You will need to pay attention to Table 4 in Chapter 23. Just for a moment, take a look at Table 4 in Chapter 23. I believe it's page 19, so you can get there rapidly. Is it page 19? I think it's page 19. A lot of wonderful information in this little table, some of which you will have to use if you intend to respond successfully to the questions, to some of the questions I've asked you on SQ3. Now then, with SQ3, it has always been my intention and desire to now continue with establishment of solid foundation for your success as a student in organic chemistry class. And time permitting, next week with our remaining classes, we'll talk about some of this stuff. But some of the questions and problems on SQ3 are purposely designed by me to force you to start to pay attention to this stuff. Much of which is discussed where? In Chapter 23. For example, in Chapter 23, we raised the issue of how can you, right off the bat, get a good start in writing Lewis pictures for organic molecules? Starting with the simplest kind of organic molecules, hydrocarbons. It's all in there. Have you read it? If you haven't, read it. It's there for your use. All right? Now then, back to resonance. As we said, it's absolutely impossible by drawing a picture to draw an accurate representation of a resonance stabilized valence structure. You can't do it by drawing a picture. Because, for example, from an arithmetic standpoint, with the CO bond orders being 1.5 at each of these CO bond sites, how the hell can I draw a picture of a half a bond? I can't do that. Or for nitrate ion, where you have a bond order of 4/3. How could I possibly draw a picture of 1/3 of a pi bond? You can't do that. I mean, some textbooks have tried to play games with dots and all this kind of stuff. To me, that's rather pointless. You simply have to understand, when you see this kind of Lewis structure construction, you're looking at a species which has resonance, which immediately rules out the possibility of your being able to draw an accurate pictorial representation of this valence electron structure. You can't do it. But it is in fact a true property of this species. So you have to be aware of it if you're going to be learning about chemistry. So, one comment with this picture before us is to show you how the various resonance forms, resonance form 1, resonance form 2, are drawn when you're dealing with the Lewis structure for a species which shows resonance. You take the atom where the Lewis structure shows negative charge, here, okay? And you take any one of these non-bonding pairs and advance it to bonding status. When you take a non-bonding pair and advance it to bonding status, what does that do to formal charge? Have you recognized this yet?
It increases formal charge.
In this case, the formal charge on this oxygen is -1 for this Lewis picture. When I play this game, what happens to this -1 formal charge? It becomes 0. So your statement is right. You increase formal charge. Now, be careful when you say increase, because a lot of people say, oh, that means it's now going to be -2. So it's an algebra game. So I think it's probably better to say it makes negative formal charge become less negative, or 0, and it makes 0 formal charge become positive, which really corresponds to increase from an arithmetic standpoint. Now then, at the instant at which we imagine this advancement, I now have a double bond here, and 2 non-bonding pairs rather than 3 non-bonding pairs. And you know that a carbon atom, because it has 4 valence orbitals, can or cannot have 5 valence electron pairs. Cannot. It's impossible. So at the same time, at the same instant at which we advance one of these non-bonding pairs to bonding status, we have to take one of these bonding pairs and advance it to non-bonding status. That's how I generate this Lewis picture. That's all you do. You go to the site of negative charge and move electron density away from that atom.
Does resonance cause the molecule to lose energy because it's going to be transferring energy from bonds to proton bonds?
Well, let's put it this way. Your comment on losing energy is correct. This thing is more stable than it would be if it didn't have resonance. But again, one way to realize this is to measure this property to which I referred a moment ago, although I didn't use the term resonance energy. If I use table 4, page 19 in chapter 23, where you looked a moment ago, and I take a carbon-oxygen double bond energy and a carbon-oxygen single bond energy, and I add those 2 values together and divide by 2, I will, from an arithmetic standpoint, have the energy of a carbon-oxygen bond with a bond order of 1.5. Okay? But if I go to the laboratory and observe the strength of a CO bond for acetate ion, or any carbon-oxygen bond that's stabilized by resonance, I'll find out this bond is somewhat stronger than that bond energy we calculated by this double bond plus the single bond and divide by 2. The difference in these energies, the actual energy showed by a carbon-oxygen resonance stabilized, by a resonance stabilized carbon-oxygen bond, between this double bond plus single bond divided by 2 is called resonance energy. And it shows you, just like the fact that these CO bond lengths and strengths become equal. Resonance is real. That's important. All right? So let's go to 2327. See these 3 acids? What are you going to do to get a handle on the relative Bronsted acidities of these 3 acids? What are you going to do? Lewis structures. Come on, let's go. Fast, right now. Zoom. So I played the game for nitrous acid. This one. You play the game for nitric acid. We've already done that. You remember when we looked at the nitrate ion? Valence electron structure? Electrochemistry? Trying to develop methods for determining equations for reactions and such. And this is hydrogen carbonate ion. Take away H plus, you've got a carbonate ion which shows a Lewis structure which is almost a spitting image of the nitrate ion Lewis structure, except that you have a carbon central atom rather than nitrogen, and a total minus charge of -2 rather than -1. Well, put them up here. Now, you can draw the other resonance forms, and you can add on the H plus if you want to show the Lewis picture for bicarb ion, the parent acid, or the nitric acid molecule, the parent acid of nitrate ion. Okay. How do these bases compare strength-wise? ENCD, effective negative charge density. And see this oxygen, this oxygen, this oxygen, this oxygen. How are those oxygens hybridized? Oh, here's another one. Now, if you play the game of looking at an atom and counting number of sigma pairs, remembering that non-bonding pairs are counted as part of the sigma system, 1, 2, 3, you would identify this immediately as sp2. The question is, how is this oxygen atom, 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 how are those oxygen atoms hybridized? Statement. I'll write it as a note. An atom with NB, P, or P's, okay, bonded to an sp2 atom. Pause. This atom sp2? 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 Central atom in these, all sp2, right? So we carry on. An atom with non-bonding pairs, or might be just one, non-bonding pair or non-bonding pairs, bonded to an sp2 atom is also sp2. Argument. You see the two Lewis pictures here for nitrite ion? And if I wanted, I could write the other two resonance forms, the other two Lewis pictures for nitrate ion and the other two Lewis pictures for carbonate ion. You can do that. The only way this atom can be recognized to also have this valence electron environment. Is for this atom to also be sp2. It must be able to participate in pi bond formation. Just like this atom, and this atom, and this atom, and this atom. So, here's this note. It's really important because you're going to be dealing with a slew of organic molecules that show this property. Or a slew of organic molecules which contain atoms that show this property. An atom with non-bonding pair or pairs bonded to an sp2 atom is also sp2. Period. So if you got a Lewis structure written correctly, and you got an atom that's sp2, like the central atoms for each of these things, to which another atom is connected, in this case an oxygen, by an apparent single bond. And that atom has got one or more non-bonding pairs, like each of these peripheral oxygen atoms. That atom ain't sp3. In this case, you've got to forget this counting the number of sigma pairs which are apparent from the Lewis picture. You've got to apply this rule. Remembering, the only way this atom could participate in pi bonding is if it is also sp2. So there's this statement that I made mention of when I was up there and told you that we were going to show you this. All right? How do these bases compare strength-wise? Which means we're asking, how do these acids compare strength-wise? Now you already know the answer to this from our acid-base table. But if you didn't have the acid-base table information before you, or you were not aware of such, how would these bases compare strength-wise? Well, let's first start with the nitrogen bases. Nitrite versus nitrate. How will these two bases compare strength-wise? Next statement. The more resonance forms for a species, the more effective resonance is for that species in stabilizing, in this case, negative charge density. Nitrite versus nitrate. Which has more resonance forms? Nitrate. Now how about induction? Aren't each of these ions bearing a total minus charge of -1? Right? They're each bearing a total minus charge of -1. But that total minus charge of nitrate ion is stabilized by 4, count them, atoms of appreciable electronegativity. But for nitrite ion, only 3. So here's induction all over again, isn't it? How about that? If I got 4 atoms of appreciable electronegativity stabilizing negative charge, compared to another species with 3 atoms of appreciable electronegativity stabilizing negative charge, I do a better job with the 4 atoms. More inductive stabilization of negative charge density by nitrate ion versus nitrite ion. One more question. What would you argue? It's easy for nitrite ion. What is the true formal charge for each oxygen atom for the nitrite ion? The true formal charge for each oxygen atom for the nitrite ion. True formal charge for each oxygen atom. Remember, these oxygen atoms are equivalent from a valence electron environment standpoint. That's what you can't show by drawing a picture. -1/2. What's the true negative charge, the true formal charge, on each peripheral oxygen for nitrate ion? -1/3. How about that? Now, what's the true formal charge for each oxygen for carbonate ion? Negative what? 2/3. Well then, isn't it obvious that a species with a formal charge of -2/3 on its oxygen is going to be a stronger base than a species with a formal charge of -1/2 or -1/3 on its peripheral oxygens? Isn't -2/3 twice the negative charge density of -1/3 from an arithmetic standpoint? That's it. And you can also put in induction, because carbon doesn't do much when it comes to stabilizing negative charge density by induction, because carbon has not got a particularly low electronegativity, not nearly as low as nitrogen, for example. size, these are about the same. Carbon's a little bit bigger. But the really big difference between this thing and this thing is that this thing is minus. And when you try to pull H plus from something that's minus, you're already fighting a tough battle. In most cases. Hydrogen sulfate ion is an exception. Hydrogen carbonate ion is not an exception. This is a lousy acid. Remember its Ka value? 4.8 times 10 to the minus 11. Whereas this is a strong acid. Its Ka value is enormous. Now we don't have nitric acid, nitrous acid, this thing, in our acid-base table, but it's got a Ka of about 10 to the minus 4, something like that. You can look it up if you want. Maybe I'll put it in the acid-base table. Who knows? All right? Now then. The principle of maximum overlap. What is stated about the principle of maximum overlap in the notes is about as good a statement as I can make to put this in words. But I think PMO is more effectively recognized or understood by Lewis picture analysis, including structure analysis. PMO in a nutshell says this applies to the greater extent when I'm dealing with species composed of atoms of large electronegativities. Now, what are the atoms that are of appreciable electronegativities? Most of them are the small atoms, aren't they? Nitrogen, oxygen, fluorine. Now, chlorine is also part of this game because chlorine has an appreciable electronegativity. So does bromine. Bromine not quite as great as oxygen, but in all tables that I've seen, the electronegativity of bromine is cited as only about 2/10 of electronegativity units, smaller than that for chlorine. In the Sargent-Welch periodic table, which you have as a gratis periodic table that I give to all of you folks in the 45L and 46L lab manual, it's got a lot of good data on there. I've told you on Special Quiz 3. I told you on Special Quiz 2 to use that table for information should you have needed such. All right? So we're going to look at two acids. These are the two acids. Now we've already done an analysis of nitric acid over here and its conjugate base nitrate ion. So let's look at this one. This is chloric acid. Lewis picture with single bonds shows this. Can I write a better Lewis picture, which means, in this case, can I write a Lewis picture where I will reduce the degree of formal charge shown by the species? Here I have -1, -1, -1, and +2. Can I do this? And if I can do this, can I do this? Now I've only formal charge on one atom, that's it. Because now, other than this atom, formal charge of these atoms all 0. There's nothing wrong with these Lewis pictures? In writing these Lewis pictures, am I breaking any rules? Am I violating any true valence electron capacities? In this case, for the central chlorine atom? Can the central chlorine atom have more than 4 electron pairs in its valence environment? Because this picture says 5. How many, theoretically speaking, how many electron pairs can be in the valence environment of chlorine atom, or any period 3 atom? 9 of them. We did this already, didn't we? End of chapter 19. And you should have done this in 2045. Well, there's no violation here. So I'm going to pick this as my best Lewis picture because it shows the least degree of formal charge. Well, this is telling me resonance. Right? Hey. But, would you argue this oxygen atom to be sp2? This one, yes. This one, yes. Would you argue this oxygen to be sp2? Is this chlorine, the atom to which it is bound, is this chlorine sp2? Well, then be careful. Better not argue this is sp2. So what we're now doing is questioning the validity of this Lewis picture as a consequence of this note we just brought to our attention. Now then, let's pay attention to induction stabilization of negative charge. Nitrate ion, all the component atoms, 3 of which are oxygens, are of appreciable electronegativity like this. And this thing is going to be a little bit bigger than nitrate ion, isn't it? Because chlorine is a bigger atom than nitrogen, isn't it? So far, I would bet that chlorate ion or nitrate ion, which one is the more stable base?
Nitrate.
Why'd you bet nitrate?
Okay, from the table.
From the table. We don't have that in our table. HOClO2. Then what? No, it isn't. No table I've ever seen shows chlorine to have a smaller electronegativity than nitrogen. They either show them equal or chlorine electronegativity a little bit bigger. Induction the same?
Yes.
Bigger central atom? So if this resonance is correct, I'm smearing the minus charge, totally minus charge of -1 over a larger surface. Doesn't that dilute the minus charge more effectively? So far it appears to me that this is a stronger acid than this. But when I look up the data, I find out that this is a hell of a lot stronger acid than this. You know, this has got a Ka on the order of 10 to the 4th. This has got a Ka, I mean, this is a pretty good acid, but this has got a Ka on the order of 1 or something like that, or power of 10. So what's going on here? We'll pick it up from this point next time.